So last time, okay, so here's where we are in the big picture. It's been a long time since we talked about physics. So for the first bunch of weeks, all we talked about was kinematics. We were just describing motions, talking about relationships between position, velocity, and acceleration. And then recently we switched over to kinetics, where we start including the causes of those motions too. Okay, so now we're on kinetics of particles. And the main equation, the most important equation in this whole class is Newton's second law. Newton's second law. I'm going to always abbreviate that N2L because I'm going to write it all the time. And Newton's second law says F net is equal to the mass of a chosen object times the acceleration of the chosen object's center of mass. With particles, the object is just treated like it's in a single location, so the center of mass thing isn't super important. But F net is the sum of all external forces acting on the chosen object. M is the mass of the chosen object. And ACOM is the acceleration of the chosen object's center of mass. Center of mass. And then, so in order to use this, we have to have representations for all of these forces. And so there were 1, 2, 3, 4 types of forces, well, I guess 5 if you include weight. 5 types of forces with known directions. Those were the weight. That was by far the simplest of all these. We already did that one. The second one was pushing contact. Can anyone remember how to describe the direction of the pushing contact force? I know this was a long time ago. So first, it's perpendicular to the surface of contact, but that only narrows it down to 2 possible directions, right? So it's perpendicular to the surface of contact. Is it toward the chosen object or away from the chosen object? Toward, that's right. So we talked about that. The third one is pulling contact. Usually we do this with cables. This is where we are right now. We've talked about cables by themselves, but we haven't done a lot of examples yet where the cables are going over pulleys. We'll do some more of that. The fourth one is friction. And the fifth one is springs. So we're in the middle of pulling contact, then we'll get to friction and springs. Anybody have any questions about kinetics? So back to pulling contact. Actually, let me go back a little bit from that. So a massless cable applies the same force along its whole length and that force is let's see, a massless cable applies the same, let's say the same magnitude of force along its whole length. And so what we still need to, that doesn't tell us, is the direction of that force vector. And the direction of the force that it applies is parallel to the cable. Bless you. And away from the chosen body. This is also true if between the ends of the cable the cable passes over pulleys. And these pulleys, these assumptions only hold if we treat the pulleys as being massless and frictionless, which is actually usually a pretty good assumption. Because usually the other forces that we're dealing with are a lot bigger than the friction force and the forces that come from the mass of the pulley. Okay, so for example, if that's body 1 and that's body 2, and let's say this is a force F. Let's draw free body diagrams of bodies 1 and 2. So free body diagram of 1. There's a weight. Call that M1G. There's a pushing contact from the ground, so that's perpendicular to the ground toward the chosen body. I'll call that N1. And then the only other place that the boundary of 1 is contacted is that pulley, that cable, I mean. And so it's applying a force like this. And then if we draw a free body diagram of body 2, that has a weight of M2G, a pushing contact, normal 2, this applied force F, and then the cable applies a force parallel to the cable, away from the chosen body, and the key thing is with this cable, the force magnitude is the same here that it is here. Okay. So now let's see what happens. So these have the same magnitude. So here's an example with pulleys. Okay, so let's say that we have a body 1 connected to a cable, and that cable goes over 3 pulleys like this, and then connects to a body 2. Between the ends of this cable, it's not touching anything except pulleys. And so that means that the rules for cable forces that hold if that pulley doesn't touch anything between the two ends still holds. So free body diagram of body 1. There's a weight force of M1G. And then there's a force parallel to the cable where it contacts this, away from the chosen body. So I'll call that T. And a free body diagram of the second body. There's the weight, M2G. And then the cable force is parallel to the cable, away from the chosen body. And the magnitude of these forces are the same. Okay, so that's what pulleys do. They can change the directions of those forces, but they don't change the magnitude of those forces. Did we do a problem last time? Can you look in your notes where we had one cart, like a rolling thing, on a ledge, and then a pulley, and then another one pulling? Okay, that was the last one we did. Okay, so I want to do, so last lab, remember the lab with the ramps and stuff? We're just going to do that lab again on Friday. I don't think anyone really understood very well what was going on. And I'm going to do the example right now. It's the calculation you have to do for the lab. Okay. So here is a new strategy that we're going to use for the rest of the class. Whenever whenever we have an object that's sliding or rolling along a surface, we're going to choose the y-axis to point directly out of the surface. And then the x-axis will be parallel to the surface. If you have something sliding or rolling along a horizontal surface, then that ends up just being our usual default coordinate system. You know, the y-axis is pointing out of a horizontal surface. The x-axis is parallel to it. So if you have a case like this, that means the coordinate system looks like that, like we're used to. If you have an object on an incline like this, and the coordinate system has the y-axis at an angle and the x-axis parallel to the surface. And if that incline is going the other way, the y-axis is out of the surface, like that. Which way is the x-axis? Down. Yep, it's parallel to the surface, but remember that there are, if you're thinking of a line, like the surface is a line in these two-dimensional problems, there are two directions that are parallel to that surface and two directions that are perpendicular. So knowing that it's parallel to the surface isn't enough to specify the x-axis direction. What you have to, in order to specify the x-axis direction in 2D, you have to think of just a rotated version of our usual coordinate system. You can't flip it. Okay, so this is our usual coordinate system. That means that if our y-axis is this way, the x-axis has to be that way. Okay. And if the y-axis is this way, the x-axis has to be that way. Because if you put the x-axis that way, that would be like a flipped version of our usual coordinate system. Does that make sense? Okay, so why do we do this? Good question. Anybody have an idea what this helps? What's the point of this? There's no reason we have to change the coordinate system. But the benefit is that a few things are going to be simpler when we do it this way. The normal force, the force of friction, and the acceleration. The acceleration vector if we do it this way, can just be represented by single components. And that's just going to simplify the math. So, like in this case, the normal force is straight up. And so you'd represent that as a vector as 0n, right? It's in the y direction. So what about this? Well, now the normal force isn't straight up, it's this way. Okay? So if we use a standard coordinate system like this, we'd have to do the trigonometry to represent n. It's not horrible, the math isn't horrible. But it's simpler if we have this rotated coordinate system, then the normal force is just 0n again. Same thing with the accelerations. The acceleration here is along the x-axis. If we rotate the coordinate system, here, the acceleration is along the x-axis. And here, with the rotated coordinate system, acceleration is along the x-axis. So it simplifies the math, that's the point. It makes one thing more complicated. So it complicates the expression for one force vector. What force vector is that? What's the force vector that gets more complicated if you have this rotated coordinate system? Gravity, yep, exactly. So gravity doesn't change because your coordinate system changes. It keeps acting down, right? And now straight down is at a funny angle with that coordinate system. And so you're going to have to use trigonometry to represent the weight force. And so if you have a force like this, and your coordinate system is like this, then you have to break this weight up into components like that and that. So that's mg. This one you could think of as mgy, mgx. Okay. All right, so let me do the example that we're going to use in lab. So let's say we have an incline of, let's make this 10 degrees. The angles and masses and stuff are going to be different tomorrow. You have one cart rolling here. Let's say that has a mass of 1 kilogram. And then you have a mass of 0.5 kilograms there. What's the acceleration of the rolling cart. We are going to use, so we're going to isolate these two bodies. And since this one is, rolling or sliding along a surface, when we analyze this one, we're going to use a rotated coordinate system. This one isn't rolling or sliding, so when we isolate this one, we're going to use a standard coordinate system. Okay? And we'll be able to come up with relationships between those variables. So first I'll do a free body diagram of the rolling cart, the 1 kilogram. What forces are acting? Someone do the easy one and then you don't have to say anything else. That's not the easy one. That's a hard one. Yes. Good job, Zoe. You did a hard one and an easy one. So the weight is 1 kilogram times 9.81. So 9.81 newtons. That's straight down. And then the normal force is like that, perpendicular to the surface toward the chosen body. And there's one more force. The cable force, yep. So that's parallel to the cable, away from the chosen body. I'll call that T. And the coordinate system that we're going to use when we analyze this is rotated like that. So now let's do Newton's second law. Let's deal with the easy ones first. The cable force is acting in the positive x direction. So that's T0. Does everyone see that? Anyone having trouble seeing how that rotated coordinate system affects these components? What are the components for the normal force? Zero positive. Exactly. And then we have to deal with the weight still, so I'll leave a spot for that. And then let's go over to the mass times acceleration. The mass is 1. What do we know about the acceleration? It's only going to have an x component. The acceleration of the hanging mass is going to be in y, but the rolling one, a y acceleration of this would be either sinking into the surface or jumping off the surface. So this has to have only an x component. Okay. So you're exactly wrong. And then, do we know whether it's going to accelerate up the ramp or down the ramp? You might have a guess, but it really could be, depending on how those masses relate to each other, it could be either way, right? Like if you made this heavier, it would roll down. If you made that lighter, it would roll up. So we're not going to ever speculate about that. We're just going to write that acceleration as A0, and the sign of A will work out for itself. Okay, and the last thing we have to deal with, it was the easy one to name, but it's the harder one now you have to think about the trigonometry. So we have a downward force of 9.81. And we want to break that up into components like this. right? Those two red vectors add up to be the black vector of 9.81. And this angle here is the same angle as the incline. So this is 10 degrees. So that means that this vector has a magnitude of 9.81 times the sine of 10. And this vector has a magnitude of 9.81 times the cosine of 10. And so the force vector has, and now look at the directions. These have to be the directions in order for those two red vectors to add up to the black vector. Okay. So this one is in the negative y direction. So the y component is negative 9.81 times the cosine of 10. This one is in the negative x direction. So the x component is negative 9.81 times the sine of 10. So we have negative 9.81 times the sine of 10. Yep.
Oh, I was just wondering, will you please explain how you got like cosine of 10 is 9 to 10?
Yeah. Just SOHCAHTOA. So you know that the sine of 10 degrees is this length divided by 9.81. And so rearrange that.
Oh, okay.
And you know that the cosine of 10 is this length over the hypotenuse, and just rearrange that. You also can do this, so you also can do this the way that we talked about before. It would be best if you could be comfortable with both of these two ways of thinking about it. But we have a vector like this, and we're representing it in a coordinate system like that. This angle is 10 degrees. And so what's the angle theta if you're going to represent this as a length times cosine and sine of an angle? What's the angle theta from the positive x-axis to this? You could go negative 100, or you could go positive 260. Either one of those would work. And that gives you the same thing as this. Okay. Yes?
Why is cosine in the y component?
Well, if you want to do, so if you like to have cosine in the x and sine in the y, you always can. And then you just have to find the angle from the positive x-axis to the vector.
I see.
But we didn't do that. We did it in terms of this angle 10 degrees, which you can also do, but then you have to think about it in terms of SOHCAHTOA. So it's sort of two ways to think about it. So two ways. Those give the same thing. Just two different ways to represent it. Okay, so I'll move this down here. We're trying to find A. The second equation doesn't have A in it, so I'm going to leave that out. And we're just going to use the first equation. And so the first useful equation that we get for this system says T minus, can someone calculate 9.81 times sine of 10? So T minus 1.70 about. Okay. is equal to A. So that's our first useful equation. And then we'll do a free body diagram of the hanging weight. So on this one, we have the weight and the cable force, that's all. The weight is 0.5 times 9.81, so 4.905. And the cable force is parallel to the cable, away from the chosen body. So Newton's second law says 0t plus 0 negative 4.905 is equal to the mass of the chosen body, 0.5. And now we have to think about the acceleration of this. If this part goes up the ramp 1 inch, where does this thing go? Down 1 inch. So if this acceleration is in the positive x direction, this acceleration A has to be in the negative y direction. Anyone have any questions about that reasoning? And so this has to be 0, negative A. And so now we can use this, get our second useful equation that says T minus 4.905 is equal to negative 0.5 A. And now we have a system of equations that we can solve. We have two equations solving for two variables. The first one says T minus 1.70 is equal to A. The second one says T minus 4.905 is equal to negative 0.5A. If you subtract those two, you get 0 plus 3.205 is equal to 1.5A. And so A is equal to, what's 3.205 divided by 1.5? 2.136. Okay, so what's the acceleration vector of the 1 kilogram cart? It's this. We just didn't know what A was yet. And so now plug it back into that. And we get that the acceleration vector of the 1 kilogram cart is 2.1360. Any questions about that? Okay, let's, are there any markers? A couple. Let me do a problem that you can work through. So let's say this angle is 30 degrees. You have a cart here. A mass here. And let's say each of these is 2 kilograms. What's the acceleration vector of the cart? Okay. So, I want to talk about one other pulley thing before we go on to friction. Um, so, I want to talk about pulley advantage. And mostly I want to talk about this because I remember when I first took physics, the way that pulleys worked was confusing to me because I remembered being a kid and my parents saying like, oh yeah, pulleys have this ability to reduce the amount of weight, the amount of force you have to apply to lift a weight. Have you ever heard of that vaguely or whatever? It's one of the some number of simple machines. Like with pulleys, you can apply this tiny little force and lift up big masses. And so then I couldn't square that with the fact that all a pulley does is change the direction of a force that the cable applies, right? That's what we've just been seeing. It just changes the direction of the force. Well, it turns out that if you rig up pulleys in a certain way, you can get this pulley advantage. You can reduce the force that you have to apply to lift something up. So I want to show you how that works. So think of these two setups. One where you have a pulley hanging from the ceiling. Let's say this mass is 10 kilograms. And you want to know what force is required to hold that up. And then the second case is this more complicated setup. So there's a pulley. You're trying to figure out this force F. And now you have a second pulley that's hanging. And the hanging pulley supports the 10 kilogram mass. We want to make it so that all of these cables, stretches of cable, are vertical. Get over there. Okay, so the cable goes from this F over the pulley connected to the ceiling, down under the hanging pulley, and then connects to the ceiling. So what is F that's required for what does it mean to hold this up? It means able to make it so there's no acceleration. So what's the F required for zero acceleration in each case? How much time do we have? Why don't you do the first one? You do this one, and then I'll do the second one and show you how that works. Okay, so what you got from this one is that F is equal to 98.1 newtons. Okay, that one's not so impressive, right? It didn't change the force at all. It just changed the direction that you have to apply the force. But so now let's go to number 2. And what I'm going to isolate is all of the hanging stuff. And I think I mentioned before that if you ever get confused about how to apply those cable forces, you can include like a little bit of the cable, little stumps of cable from where the cable touches things. So we have a downward weight force of 98.1, and then go around until you get to 2 contact points. And those are the 2 places where the cable touches the pulley. Right? That makes sense, right? And now the cable force points right out of both of those stumps, and the magnitude of that cable force is the same everywhere because all it's doing is going through pulleys. So those are both T. Okay. And so Newton's second law says 0T plus 0T plus 0 plus negative 98.1 is equal to 0. And so 2T minus 98.1 is equal to 0. And T is equal to, well, F and T are the same thing, is equal to 49.05 newtons. So with this system, it took half as much force to lift the mass. Awesome! And I think probably if you had to just guess, you know, like, I think my first reaction when I saw this is like, it looks like a trick, like something weird happened in the, you know, like this is a trap to try to make us believe. But this is actually how it works. And I was saying, who put it in, you put it in your calendar to remind me tomorrow that we're going to rig this up, and you can actually like rig up pulleys this way, and you can just feel like it takes half as much force to lift something up. And if you can rig this system up with more and more pulleys with the same idea and keep reducing that weight. The trade-off is, you know, usually you don't just want to hold something up, although I suppose there are times when that's all you need, but usually you want to lift something. And this is still really useful in a lot of cases, but if you want to lift something, look back at the system here. Okay, so with this one, if this F pulls down an inch, where does this mass go? Up 1 inch, right? Think about this one, this more complicated system. If you pull this end down an inch, how far up does this one go? It only goes up half an inch. You can think of it as like, to get an inch from here, you're taking an inch from this part and an inch from this part, you know? And so the weight is cut in half, but the distance you have to pull is doubled. And if you rig up more pulleys and reduce the weight to like 1/8 of the weight of the thing you're lifting up, you have to pull 8 times as far to get this to go up. And who was it yesterday who was like, oh yeah, it's sort of like bike gears. Was that Keegan? Yeah, it's the same idea as that. And I hadn't really thought of it that way before, but you know, with your bike gears, when you gear down to go up a hill, you're reducing the force that you have to apply by a certain fraction. But the downside is you got to spin your pedals more to get as far, you know, and that's what's happening with this too. Any questions about that example? Okay, let's talk about friction. So now, go back to the list. Forces with known directions. got weight, pushing contact, pulling contact, friction, and springs. So now we're done with weight, pushing, pulling, and so now we have to talk about friction when objects are sliding. And you know the experience. I think you've probably noticed this before. Like if you're trying to push a big heavy box across the floor, it's harder to get the box moving than it is to keep it moving. Have you noticed that?
Yeah.
And so there's a different kind of friction that happens when something's sitting there still than there is when something's moving. Like once you get this big heavy box moving, you're like you want to keep it moving because you know when it stops, it's going to be hard to get it going again. So there are two kinds of friction. Static friction, when an object is at rest. And kinetic friction when an object is moving. And so there are little differences in the ways we have to treat these two kinds of friction. In either case, let's say an object in contact with the surface can have two kinds of force. The first one is the normal force. That's the pushing contact between the object and the surface. And the friction force that's parallel to the surface. What about that pushing contact? How does that direction relate to the surface? Yeah, that's right. So it's just like the stuff we've been doing, perpendicular to the surface. Okay, so let me talk about the two different kinds of friction. So first I'll talk about static friction. So when objects are at rest relative to each other, static friction prevents them from starting to slide. So the force of friction, FF, has whatever value is required for the acceleration to be 0. Up to a maximum magnitude of FF equals, that's the Greek letter mu, sub S times N, where mu sub S is the coefficient of static friction and that's something you can Google or look up in tables or whatever. It's just a property of the two materials, so you could look up the coefficient of static friction for like wood and concrete, or wood and ice, or steel and iron, or whatever. Coefficient of static friction for two materials in contact. And N is the normal force, the pushing force, between the two objects. Okay, so let me do an example. First, does anyone have a sense of why it's harder to get an object moving than it is to keep it moving? Like, what's sort of an explanation for that? Like even when things seem perfectly smooth, the two surfaces have, like, if you looked in a microscope, it's not perfectly smooth. Obviously, there's little lumps and bumps. And if you let two things sit, those lumps and bumps find their way to entangle, sort of, And so if something comes to rest, all those little bumps, miniature Legos pop into place, and it takes an extra amount of force to pop those free. When it's sliding, those little things don't have time to engage with each other. Okay, so all right, so let's say that there's a 10 kilogram box, and you apply 40 newtons like that, and 20 newtons down, and the coefficient of static friction between the box and the ground is 0.4. Oh, I didn't say that. Here, go back up to your notes for a second. This coefficient of static friction, let's think about the units for that. So look at this equation. It relates the force of friction to the pushing contact. What have to be the units of that coefficient based on this equation? Or lack of units? Because the force of friction has units of newtons. The normal force has units of newtons. And so the only way that would work out, the units would work out, is if that coefficient is just a pure number. Okay, like if it had units of meters, you'd be saying newtons equals Newton meters, and that can't work. Okay, so This is just a pure number. And it's usually under 1, but it doesn't have to be. Like rubber on concrete, I think a lot of times has values over 1, even over 3. So the question here is, with this given coefficient of static friction, does this box start to slide? So the way we're going to do it is we're going to calculate the force required for this not to slide. And then we're going to see if that's possible using this equation. Okay. So, step 1, calculate the force required to stay at rest. So I'll draw a free body diagram of the box. We have the weight of 98.1. We have the force of 40 newtons, the downward force of 20 newtons, the normal force, that pushing contact. And then if this is going to keep from sliding, we know that the friction force has to be acting this way to counteract that 40. So I'll call that force of friction. Then Newton's second law says 40, 0 plus 0, negative 20 plus 0, negative 98.1 plus 0n plus force of friction is in the negative x direction is equal to the mass times acceleration of 0, so just equal to zeros. And so what we get is that the force of friction has to be equal to 40 newtons. Well, after you see that answer, you're like, well, yeah, obviously. So now we're going to see if the maximum possible value of friction is smaller than this or bigger than this. If the maximum that this friction can apply is smaller than this, that means this box is going to move, If the maximum friction that can be applied between these two objects is bigger than this, then the friction can handle this requirement and it's not going to move. You understand the reasoning on that? Okay, so now step 2, find the maximum friction magnitude. We're going to use this equation that says the force of friction is less than or equal to, or let me say, the maximum is equal to the coefficient of friction times the normal force. We can use this second equation above to calculate that the normal force, we have negative 20 minus 98.1 plus n is equal to 0. So n is equal to positive 118.1. Look, I named this friction force after you. And so the maximum force of friction is equal to the coefficient that was given, 0.4, times 118.1, which is 47.24. Okay, so the force required to keep it at rest is smaller than the maximum allowable friction. So does this stay at rest or move? Stays at rest, yeah. If you're checking to see whether the friction can handle the requirement to stay at rest. So force of friction can handle requirement for zero acceleration. So it stays at rest. Any questions about that? Let's stop there and we'll do kinetic friction next time. Yep. Oh yeah, quiz. Yeah, up to including this stuff. Oh yeah, this is the only class, isn't it?
Yeah.
Let's skip the quiz tomorrow. Okay. So, and we're redoing that lab tomorrow. Thank you.